welcome from Coulomb, England, where I am at my conference. Thought I would record this lecture outside. It's a little windy, so don't worry if my notes get blown away. I will run after them and retrieve them all for you. Let me show you, just to prove that I am where I say I am. Let me turn this around. Let me put it the right way up. There we go. And turn it around. That is Coulomb Radio Telescope, where the conference is. Okay. What I want to do is just give you a few hints and tips that you can use when using Coulomb's law and solving problems involving Coulomb's law. So if you remember in class, we went through an exercise where we estimated an order of magnitude number for the amount of static charge that you can get by rubbing a balloon against hair or a sweater. So the static charge we came up with was round about 10 to the minus 7 coulombs. Generally, everyday situations, the amount of static charge you encounter is in the ballpark 10 to the minus 9 to 10 to the minus 7 coulombs. Okay, 10 to the minus 9 coulombs is otherwise known as a nanocoulomb. Okay, so you'll see that a lot of problems tend to involve charges around a nanocoulomb. If you try really hard, you can probably get a static charge up to at most 10 to the minus 6 coulombs. Right? And this is 1 microcoulomb, which is written like that, using mu, which is Greek letter M for micro. Okay, so this is kind of the range. The most charge you're ever likely to encounter in real life is around 10 to the minus 6 coulombs. Sort of a safe bet, if you just want a number to compare to, is around 10 to the minus 9 coulombs, 10 to the minus 8 coulombs. Okay, I've had to move indoors because it started raining, typically. So we were discussing typical amounts of static electric charge that you get every day. And we derived this by assuming a force of around 0.1 newtons holding up the balloon that we charged statically and then stuck to the wall. And we made the pretty drastic approximation that the balloon and the wall could be treated as point charges. And those are probably the biggest flaws in that analysis. And that means that we should treat it with a grain of salt. But we end up with the right order of magnitude. So this force of 0.1 newtons was produced by two objects. We said, if you remember, that the balloon was about 10 centimeters from the wall, the center of the balloon, that is. And we said it had a static charge of 10 to the minus 7 coulombs. So if you had, for example, a charge of around 10 to the minus 9 coulombs, okay, or just 1 nanocoulomb, let's get used to using the nano prefix, then we had two charges that had this charge, and they were 10 centimeters apart. How big would the force be there? Well, you know Coulomb's law. Okay, and Q1 and Q2 are both equal to, we call them both Q and set them both equal to 1 nanocoulomb if they're both the same charge. This is K Q squared over R squared. So you could plug in the numbers and calculate the force. But if you're doing that, then you are wasting a lot of time and effort. Okay, you need to make use of a very useful skill, that of proportional reasoning. Okay, so what we note is that we know we have a reference force of 0.1 newtons, and we know that this was derived with Q equal to 10 to the minus 7 coulombs and R equal to 10 centimeters. Now, if we just want to change Q from 10 to the minus 7 to 10 to the minus 9, or 1 nanocoulomb, we don't have to go through, plug in all the numbers again. Right, we just need to know the dependence of the force on Q, and it depends on Q squared if the two charges are the same. Right, so what have we done to Q to go from 10 to the minus 7 to 10 to the minus 9 coulombs? We've gone down to our orders of magnitude, so Q has been divided by 100, right? Which means Q squared has been divided by 100 squared, which is 10,000, right? Which is 10 to the minus 4, or 10 to the 4. So this is the same as multiplying by 10 to the minus 4, okay? So an R, we're still saying that R is 10 centimeters. So if we've divided Q by 100, then the force is going to decrease by a factor of 10 to the 4, right? So we immediately know that all we have to do is divide 0.1 by 10,000, and our new force is going to be 10 to the minus 5 newtons in that case. Okay, what happens if R is 1 centimeter now? Okay, we keep Q fixed at 10 to the minus 9 coulombs. We change R from 10 centimeters to 1 centimeter. Well, we've gone down by a factor of 10. Okay, so again, looking at the proportionality between F and R, if R itself we've divided by 10, then R squared is divided by 100, okay? And if the denominator is divided by 100, then the entire thing is multiplied by 100. Okay, so if you decrease the denominator of a fraction, you increase the number overall, and so the force is going to be multiplied by 100. So we're going to go from 10 to the minus 5 to 10 to the minus 3 newtons. Okay. This is a skill I want you to know and practice. This is this is a skill I consider to be extremely important. So you need to practice this and learn it. And a lot of problems can be shortened this way. Okay. There will be times where on an exam you do not have time to plug in all the numbers to that equation. Right? I will have designed the question specifically to be done this way. So make sure you practice and get used to it. And if you need practice and you need help getting used to it, please come talk to me or Lauren or Connor or anyone else who can help you. So this, just to remind you, this is proportional reasoning. Okay, so you now know, by the way, that the force between two charges that are, if the two charges are of order nanocoulombs and the distance between them is of order centimeters, then the force between them has a magnitude of around 10 to the minus 4 newtons. Okay, so this is another reference number to go along with your reference charges for everyday objects. It's best to pick one. I would go with a nanocoulomb for a rough estimate of charge and 10 to the minus 4 newtons as a rough estimate of force. Okay. The next tip I want to give you is how to avoid confusion when dealing with, or when switching between dealing with the magnitude of the force and the direction of the force, and what to do about the magnitude of the charge. When do you need to include minus signs for negative charges in your equations. So I'm going to outline the procedure that I follow. So let's have an example problem. Let's take 2-point charges. Here they are. Let's say one is minus 9 nanocoulombs and one is plus 2 nanocoulombs. And let's say that they're 3 centimeters apart. And I'm going to call this charge 1. So let's label this Q1 and label this Q2. Okay. So what you should do if you want to calculate, if you're trying to calculate the force between a pair of charges, and the thing to do first is calculate its magnitude. How big is the force? Right, worry about the direction in a minute. So we indicate that we are focusing on the magnitude either by putting the magnitude vertical lines around the vector force, or just calling it F without the vector sign on at all. Both of these are acceptable ways of indicating that you're dealing with just the magnitude, the size of the force. Okay. Another really good habit to get into, and it can avoid so much confusion, is always in a subscript write down what is causing the force and what is the force acting on. So let's focus on the force acting on charge 2 from charge 1. So this is the force of 1 acting on 2. Okay. It helps remind us that a force always involves a pair of particles. Forces don't come on their own. There's always something causing the force and there's always something receiving the force that the force is acting on. And you always need to be clear which is which in any problem. Otherwise you're going to run into trouble. Okay, so when you're dealing with the magnitude of the force, then you should always write down the magnitude of the charges in the equation for Coulomb's law. Okay, so it's Coulomb's constant K times the magnitude of Q1 times the magnitude of Q2 over little r squared. Okay, what does this mean? Well, let's write in the numbers. We've got 9 times 10 to the 9 Newton meter squared per Coulomb squared for Coulomb's constant. Q1 is minus 9 nanocoulombs, but when I put the magnitude sign around it, then I just treat it as a positive number. So magnitude just means make it positive. So it's 9 nanocoulombs. A nanocoulomb is 10 to the minus 9 coulombs, so don't forget that. Okay. Q2 is already positive, so we don't have to do anything extra there. So the rule is, if you're calculating the magnitude of the force, just write down the magnitude of the charges. Don't bother with any. If any of them are negative, then leave the negative sign out. And we're dividing by r squared. R is 3 centimeters, which is 0.03 meters, and that gets squared. Okay, this is something you can do in your head. Every single one of you can do this in your head without using a calculator. And again, I urge you to practice this, right? We use calculators too much, we become dependent on them, and if we do that, we lose a feeling for numbers, for dealing with numbers, and for getting a feel for how big numbers are. So how do we do this in our head? Well, again, we can break it down into some simple steps. Firstly, I'm going to write the whole thing out again, but I'm going to multiply out the 0.03 squared. So 0.03, remember, let's write it up here, 0.03 is 3 times 10 to the negative 2. Okay, so when we square that, then written in scientific notation, you square the number in front of the power of 10, so that's 9, 3 squared is 9, and then you square the power of 10, which means doubling the exponent. So we've got 9 times 10 to the negative 4. Okay, now the next step, so once you've multiplied out everything that's in parentheses, then you can start cancelling anything that will be cancelled. So for example, this 9 cancels that 9, because 9 divided by 9 is 1. 10 to the 9 here times 10 to the minus 9 here is just 1. So in other words, these cancel. Okay. On top, we're left with 9 times 2, which again, you can all do that in your head. 9 times 2 is 18, times 10 to the minus 9. And on the bottom, we're just left with 10 to the minus 4. Okay, 10 to the minus 9 divided by 10 to the minus 4, or you subtract one exponent for the other. Minus 9 minus minus 4 is minus 9 plus 4, which is minus 5. So the answer is, it is 18 times 10 to the minus 5, or if you like, 1.8 times 10 to the minus 4. What units is it? It's force, it's newtons. Okay? Let's check whether this is a sensible magnitude, right? What were we dealing with? Well, what do we know a sensible magnitude should be? We've just been over this. We know that if you have two charges that are around a nanocoulomb and they're separated by around a distance of order a centimeter, then the force should be around 10 to the minus 5 newtons. What have we got? Well, this charge here, Q2, is close to a nanocoulomb. 3 centimeters is close to a centimeter. 9 nanocoulombs is about 10 times bigger than 1 nanocoulomb. So one of the charges is the same as we used to get this approximation. But one of them is 10 times bigger. The distance is about the same, and so the force should just be 10 times bigger. So we expect the force in this question to come out of order 10 to the minus 4 newtons, and it is. It's 1.8 times 10 to the minus 4. So we are happy at this answer. It looks good. Okay, now you've got the magnitude of the force, you need to deal with the direction of the force. Well, remember Coulomb's law says, firstly, that if this is Q1, this is Q2, the force acts along a direction. The direction is along the line that joins the center of the 2 point particles. Okay, so it's going to be, they're going to be directed along this line. All we need to know is, are the forces directed away from each other or towards each other? Well, again, we know from Coulomb's law that if they are opposite charges, they attract and they're going to point towards each other. If they are the same charge, then they are going to repel and they're going to point away. Well, one is negative, one is positive, so they're opposite charges. So these are the forces. This one here is F of 1 on 2. This one here is F of 2 on 1. We calculated the magnitude of F of 1 on 2. It was 1.8 times 10 to the negative 4 newtons. Okay, F of 2 on 1 is going to be the same in magnitude from Newton's third law. Okay. Now, finally, let me just mention, this is something that can cause confusion. I've seen cause confusion quite often. Suppose, let's draw a line under that. Suppose you've got 3 charges. Okay. Let's say one is negative, one is positive, one is positive. Okay. Let's label them Q1, Q2, and Q3. Okay. Now, for two charges, we have one pair of forces. Okay. For 3 charges, then we have as many pairs of forces as there are pairs of particles. So these 2 are a pair of particles, a pair of charges. So are these 2, and so are these 2. So we're going to have 3 pairs of forces in total in this situation. Okay. What do they look like? Well, let's take this pair of charges. They're opposite, so the forces are going to be pointing in towards each other. This is F of 3, or was it 2 on 1, and this is F of 1 on 2. Okay. What about this pair of charges? Well, they are the same charge, which means they must be repelling. Okay, so this is F of 3 acting on 2, and this is F of 2 acting on 3. Okay, and then finally, these 2 charges are opposite charges, a negative and a positive, so they are attracting This is f of 3 on 1. This is f of 1 on 3. Okay. Again, notice, of course, that in any Newton's third law pair of forces, the subscript on one of the forces is just the subscript on the other, but flipped around. F of 1 on 2, F of 2 on 1. Okay, so you've got 6 forces, there are 3 pairs of forces. Each single particle has 2 forces acting on them, okay, which again makes sense. This particle here, this charge, has a force acting on it from this one and a force acting on it from this one. Okay, now it's very easy to, I've seen students get confused about which forces are which, and usually that's because they're not labeling their forces with subscripts, and they're trying to, you look at this diagram, there are 6 forces, right? Usually, if a question gives you 3 charges, the question is almost never going to be asking you to calculate all 6 charges on all 6 forces on all 3 particles. It's usually saying calculate the force, the total force, say, on charge Q2. So if you're doing that, then when you draw your picture of the situation, don't bother drawing these forces, because you're just going to confuse your picture. Just focus in on this one charge here and draw your 2 forces. Okay. And you can tell one is directed towards Q1, that's the force coming from Q1. One is directed away from Q3, that's the force from Q3. So you don't need to draw every force or think about every force in a situation. Right? You're usually focusing on what is happening on one particular charge or one particular object. Okay. So again, you can figure out the magnitudes of these 2 forces, and you can figure out the directions, and then to add them together, you need to put up your own set of coordinate axes. Okay, so you might decide to set an x coordinate up in that direction and a y coordinate up in that direction. Now, of course, again, this is a nice illustration why you want to draw nice big diagrams, right? This diagram is taking up a third of the page, and I've already got it squashed in one corner, right? If I get something like this from you, you're not going to get points for that from that part of the rubric for drawing your picture. Make sure you take up a lot of space and make sure it is clear and avoids things getting squashed like this. You can take this as an example of what not to do. Once you've set up your coordinate axes, this is now just a problem on adding vectors together, and this just becomes, pretty much the same as the vector problem I went over in the previous lecture and the vector problem you did in class.